You got it? All right. I will begin. Dear Father, we thank you for this day. Thank you for these students, for the current lack of a fire alarm. Help us to enjoy this time and to glorify you what we do, Lord. In your name I pray. Amen. All right. Let's see here. So we have actually already introduced the concept of a direct product. All right. So we talked about the so-called product group, right? You guys remember? We have group G1, and we take the Cartesian product with group G2. This is the set, x1, x2, let's say, such that x1 is in G1 and x2 is in G2, right? This is what I would call the external direct product of G1 and G2. So I'm assuming that G1 and G2 here are groups, and that we do the group operation in each component one at a time, right? Separately, independently. I mean, G1 could have addition, G2 could have multiplication, et cetera, et cetera. We've studied this group, right? So the new thing is to talk about an internal direct sum. Internal direct product, rather. So internal direct product would be something like when G is isomorphic to H cross K, something like this, all right, where H and K are themselves subgroups of G. So if we can understand G as the decomposition of essentially looking like the Cartesian product of two of its subgroups, all right? If that's the case, then G is said to be formed by the internal direct product of H and K. The difference is in the isomorphism versus equality, all right? External direct product is literally the Cartesian product of these two groups. All right? Internal direct product just means that there exists an isomorphism, right? So you could rewrite the group if you change notation in some sense through this isomorphism, right? As a direct sum, a direct Cartesian product of H and K. So that's the big topic for today. Let me give you a definition. And this definition, so this was not the definition. This is actually intuition. The definition is not going to look immediately like that. The definition is going to look somewhat divorced from this at first glance. Here's the definition. If G is a group, all right, and subgroups H and K of G with H intersect K being the identity, set containing the identity, and H direct sum, direct product K equals to H times K, such that H is in H and K is in K. All right. If that is equal to that's equal to G. So if we have a group, if we have a pair of subgroups H and K, they intersect at the identity, and I think there's a typo here actually. Well, that's fine. Then we say G is internal direct product of H and K. I'm a little bit worried about this definition. All right. Now, in the case that we're working with an additive group, we probably wouldn't say internal direct product, right? We would instead say internal direct sum, right? But annoyingly, we just use the symbol plus circle for both internal direct sums and internal direct products in here because I don't have a good notational solution otherwise, all right? If you look at a book like Galean, Galean also uses plus circle for this, which I think adds another level of confusion altogether. So let's not do that. I like our external direct products to just be like this, yeah? But there's a lot of different notational choices out there. All right, so a quick example. Before I go on with the general stuff. If we look at G equals to Z mod 6, yeah, then we can look at H, the subgroup generated by 2, which has order what? 3, yeah? And we can also look at the subgroup generated by 3, which has order 2, yeah? And if, okay, here's the, I just figured out, I know what's bothering me, I know what the typo is. This is an important typo, I'm pretty sure to correct. Now, you stick with me through the lecture, we'll decide whether or not I need to come back and undo this, but I'm pretty sure for this to make sense, that needs to be normal for this concept here. They're supposed to be normal subgroups. All right. Now, this H and K for Z6, are those normal? Well, it's an abelian group, right? Every subgroup is normal. So those they're normal subgroups. Where do they intersect? 0, right? By the way, you could, independent of this data, independent of the data that's here, you could define the product of subgroups, right? So we have a meaning HK is by definition the set HK such that H and H and K. That's how we define the product of subgroups, yeah? Like that. So, you could ask questions like, is the product of subgroups a subgroup? Right? I don't know. Maybe. Sometimes, for sure. All right. So here, getting back to my example, what is HK in this madcap? I mean, that really, maybe we would write as H plus K in this context, yeah? Maybe I should put quotes around this. I don't know. Because I'm talking about the sum of the two subgroups, which would be the analog of the product of the two subgroups, since we're in the additive context. What is this, all possible sums taken from those two sets? Yes, oh no, what's the problem?
No, I'm just wondering how that is different from that, or is it just different notation for the same thing?
This carries with it the rights and responsibilities of, this notation is a shorthand for G is the internal direct product of H and K. So like, when I write plus circle HK like that, that says a few things. That says that H, I think you could justifiably interpret that to say that H and K are normal, that they intersect at the identity, and that their product is all of G. You're right, this is literally HK as well, yeah. Hopefully, as the lecture goes on, we will clarify and come to terms with these concepts. Let's see. Okay, so if we take the sum of all possible things in those two, what do you get? You get the whole thing back again, right? So if I take, I got 0, 2, 4, 0, and 3, because those are just literally things in there. And then if you add these two together, what else do you get? 2 plus, like 4 plus 3 is what? It's 1. And is that everything? I think it's everything, yeah? Oh, I've listed 0 twice. The dangers of working with multi-sets, right? Let's see here. 3, 1, and 5. Okay, there you go. Anyway, so the point is, the direct product, if you will, or excuse me, the product or the sum, if you want to. I mean, this is in the very abstract sense, a product, but I'm not a fan of that language, actually. I'd like to say that this is the sum of h and k. I think that's a better description of what we're doing. It's everything. It's intersection 0. So yeah, G is what? All right, so my point is that G is equal to H plus circle K, okay? Because I've shown that you can build everything in G from it. Their intersection is 0. They're both normal. We have met the terms and conditions of my initial definition. And again, this is a transitional definition in some sense because the real definition is stated right here. This is probably the definition that we should stick with long term. Yeah.
So when you say H cross K, do you mean that in the same way that you mean G1 cross G2? Because
there's an isomorphism there. I'm not saying they're equal. Notice there's an isomorphism. But yes, when I say H cross K, I mean the direct product, the external direct product of H and K. So a subgroup is the internal direct product of its subgroups if it's isomorphic to the external direct product of those subgroups. Okay, moving along here. Let me show you what happens. Let's see what happens when we don't have normality of the subgroups and we try to do what we just did, okay? I want to show you that if we don't meet the terms and conditions of my current definition, that the thought bubble, the thought cloud there fails, it breaks down for this example. So this is example 3.38. It's just a cautionary tale, if you will. And so we're looking at the dihedral group D3. And for the purpose of this example, I'm going to use 1x, x squared, and y. Apparently, oh man, this is unfortunate. This is my old notation, or an alternate notation for D3, right? What have we been writing in here this year? We've been writing what? E, A squared, B, BA, BA squared, yeah? So that's our D3. These are equivalent. In some sense, it's got these two things flipped over in the ordering. All right. Anyway, I'm going to stick with the XY notation as to confuse you. So here we go. We can think about the subgroup generated by X, which of course is 1x, x squared. We can think about the subgroup generated by K. Well, we can think about the subgroup generated by Y, yeah, which is just 1 and Y. All right. So we've got two subgroups, yeah, and you can try it out. I mean, actually, this is pretty obvious that if we take the product of the X subgroup and the Y subgroup, in other words, H times K, if you think about what that means, that's all possible products of powers of X times powers of Y. That's D3, right? So certainly the product of these two subgroups is D3 again, right? And the intersection of H and K, I should probably fess up, this one's H. So H intersect K is what? It's just 1, right? So far so good. Product is everything. They intersect at the identity, but normality. What about normality? Well, hey, X is normal, right? Is H a normal subgroup? Tell me why H is a normal subgroup of D3. What's that? It's half the order, right? The index of H is 2. So that makes it normal by theorem we saw last time. And if that was guessing, good guessing. So let's see here. I'm reading into the happiness. Let's see here. Now, I could be wrong. I shouldn't make assumptions. All right. On the other hand, if we look at xk versus kx, what do we get? Xk has got in it x and xy, and kx has got in it x and yx. So kx is not equal to xk. So k is not a normal subgroup. All right? And what I want to argue for you is that because there's this departure from normality, when we look at the product of h and k, all right, it's actually not going to be isomorphic to h cross k. All right? In other words, what I'm trying to say is that D3 will not be isomorphic to the external direct product of these two subgroups. Let's see why these are different. So if we think about h cross k, one of the things that makes it special, right, that's the set of what? H comma k, such that what? H is in H and k is in k. Can you guys tell me, how can I construct an element of order 6 in h cross k here? One of order 3 and one of order 2. Very good. What would those be in our current notation? X, yep, x and y. This says that the order of G is 6. So it has an element of order 6. How big is h cross k? What's the order? Order of h cross k is what? How big is it? You have the Cartesian product of two finite sets. How big is it? It's the size of one times the size of the other. 2 times 3. Yeah? Well, 3 times 2 in my current. Jibber jabber. Yeah? So that's 6. We've got a set of order 6. It's got an element of order 6. What is this set? It's a cyclic group of order 6, right? So therefore, h cross k is isomorphic to Z6, which of course is not isomorphic to D3, which is, by the way, equal to the product of h and k. So you see, the normality, well, the lack of normality of k has ruined it. It has made this dream of the external direct product of the subgroups matching the given group an impossibility. They're just different. All right. So this is a cautionary example, all right? It doesn't really help us do much except to understand the definition a little bit more deeply and the fact that the normality for both of them is necessary, right? It's not enough. You can't, I mean, this has one of the subgroups normal and it still fails. You have to have normality of both. Now, so let's do the groundwork here to get to the thought bubble, so to speak. So if we have h and k normal subgroups of G, all right, and they intersect at the identity, then we get some really neat calculational tools. All right, here's the calculational tools that entitles you to. Part 1, if we have A prime in H and B prime in K, such that A, B equals to A prime, B prime, then what's the punchline? Stupid watch. Give me the time, idiot. Worthless. Ah. Grief. Oh, yes, A equals to A prime and B equals to B prime. Part 2 says that if A is in H and B is in K, then they commute. AB is equal to BA. All right? This is the lemma. Once we have this lemma, it's a simple matter to actually use the data in the definition to produce the isomorphism in my thought bubble definition. Yeah? All right, so let's prove this lemma. This is actually kind of the biggest point of the lecture today. Yeah?
So on that board where it says where H and K are subgroups of G, do they have to be normal subgroups, or does that not matter?
In the thought bubble?
Yes.
No, they don't have to be. There is no, I mean, well, I suppose that's what we're getting at. Yeah, fair enough, fair enough. It's just, the reason I waffle on that is it's less dangerous to not put normality there. Not putting normality down here is troublesome. See, because if I didn't have normality here, right, I would still have that H times K is D3, yeah? I would still have that they intersect at 0. But it would no longer be the case that HK is isomorphic to H cross K, which is what I'm ultimately after. So yeah, I should put normal there. Okay, so proof. All right, what are we assuming here? We want to assume that A is in A and A prime are in H, B and B prime are in K, and then we start with what? Suppose just what I said, right? Where, what else do we want? AB is equal to A prime, B prime, right? Let's see here, notice. Let's see here, how can we work with this? If I take the expression that I'm given, right? And let's say I'm trying to think what I want to do here. Let's see here. What do we know about? Let's write down what we know about the normality. So we have that to work with, right? Normal subgroup of G implies what? That implies GH. G inverse is a subset of H, right? For all G in G, yeah? And K, a normal subgroup of G, implies that GK, G inverse is a subset of K for all G in G, yeah? So that's what normality entitles us to. We should try to use that. Yeah? Any thoughts? I think I'm going to take star and try to solve for B, see if that gives me any insight, yeah? So observe. Maybe I could, here, let's try this. A, B, H equals to what? I'm actually going to work with the other viewpoint for a second here, see if it helps us. So ABH is equal to AHB, yeah? Yeah, I feel like that's going nowhere too. Sorry. I could look at my notes, but that's admitting defeat. Let's see here. All right, let's try to solve for b like I said. How would you solve for b? B equals to what? B is equal to A inverse A prime B prime. So what does that say about A inverse A prime B prime? This is an element of, what is it? K, yeah. Well, wait, you said K? Oh, because where's B? In K. All right. Which implies what about, what does that imply from star? Oh, but B prime is where? Is an element of K. Well, how about this then? Why don't we multiply by, so B times B prime inverse, which is equal to A inverse A prime, is an element of what? If we take an element of K, which was right above, right? And we multiply by the inverse of an element of K, what do we have? By closure of the subgroup, we have that this is also an element of K, right? Did you guys follow me? So nobody had trouble with the top one because B is in K. Then, because we're looking at something we don't have a full understanding of where it's at, this part, yeah? I mean, we know that's an H for sure, right? We know the thing I just circled is an H. That's not up for grabs because it's a product of things in H. When we multiply it by something in K, like, what's going on here? But if I multiply by the inverse of B prime, that isolates A inverse A prime, which is something, by the way, that's clearly in H. But now, since it's a product of things in K, it's also clearly in K. So therefore, A inverse A prime equals to B prime inverse is equal to what? Well, let me point it out. It's an element of H intersect K, right? But what did we assume about H intersect K? That's the identity. So what did we just learn then? Hence, A inverse A prime equals to E, and B prime inverse equals to E, which is to say that A is equal to A prime and B is equal to B prime. What is so funny? You guys are very, very selfish. You find jokes and you keep them. You don't share them with me. It's not nice. I share my jokes for the most part. I mean, barring political correctness, of course. But you know. Hashtag don't want to go to jail. Hashtag I don't know. All right. So that's one. All right. So we've proved one. How do we prove two? So again, for 2, let A be in H and B be in K. Consider AB equals to BA, yeah? If and only if what? AB times BA inverse is equal to the identity, right? If and only if what? We can trade that for A inverse, B inverse equal to the identity, right? if I call the thing I'm looking at, notice, x equals to AB, A inverse, B inverse is equal to the identity, which, I've already got that, is an element of what? It's an element of H intersect K, yeah? Right? Because it's the identity, which is H intersect K by assumption here, yeah? So then what can I do? I can use normality, right? That means that AB, A inverse, B inverse is an element of H, yeah? And AB, A inverse, B inverse is an element of K. I'm not sure this helps. It's things are true, yeah? I'm really hoping we get AB equals to BA out of this sometime soon. Oh, wait a minute. Do I already have it?
I think you assumed.
Yeah, you assumed it.
Oh, I assumed it, yeah. So what the chain of equivalences shows that is if we could show that AB, A inverse, B inverse was equal to the identity, then AB is equal to BA, right? But showing that AB, A inverse, B inverse is equal to the identity seems possible, given the data. Let's see here. All right, so what I wrote down I think is true, but I'm not sure this is helpful to that goal, so I'm going to erase it, yeah? Let's look at it this way. Notice that B, A, B inverse, words. A, B, A inverse is an element of A, K, A inverse, which is a subset of K. So therefore, A, B, A inverse is in K. Right?
So we're just going to continue with assuming AB could be a...
No, well, I'm given that H and K are normal subgroups. So at the moment, I'm just using normality of K to point out that conjugation by A of B gives me something that's back in K again, right? And I can do the same. I can play the same game. See, I just played that game with this piece, right? But I could play that same game with this piece, yeah? So I also know that B, A inverse, B inverse is an element of B, H, B inverse, which is a subset of H by normality. Therefore, B, A inverse, B inverse is an element of what? H, yeah?
Should A and B, should A be not inverse? Should it just be normal? Or should it be B, A, B inverse instead of B, A inverse?
Well, I'm looking at B, A inverse, B inverse because that's what's up here, but I guess you could look at that too. I mean, you're not wrong. I mean, I could erase the, do you want me to erase the minus? We erase the minus.
No.
I'm not sure it helps or hurts, but we could erase the minus. Definitely could erase the minus. We could leave it. Yeah.
So are we assuming that AB equals BA? Because that's what you're trying to show, right?
I have not assumed that AB equals BA yet. What I'm trying to show is that AB, A inverse, B inverse is necessarily in both H and K, and therefore must be in the intersection and must be equal to E.
So the two lines that are written there is what we're trying to get to?
Right, I will refer to this chain of equivalences in a second. We're not done. So I should probably put a period here for the moment, yeah. So what do we have? We have that A, B, A inverse is in K. We have that B, A inverse, B inverse is in H. Can you guys tell me how to get from those to A, B, A inverse, B inverse? Oh, maybe I don't. Look, I'm making my life too hard. Do I need even the thing in purple? No, I don't. I don't at all. Forget about it. I mean, just, you don't have to erase it. Just, it's fine. But notice that if we have that A, B, A inverse is in K, and although maybe I'll need that in a second, and you're like, make up your mind already. I know, fine. B inverse is in K, right? So therefore, a seldom known mathematical construction, not to be confused with therefore. So therefore, which is a tired professor's therefore, but A inverse, B inverse is also in K, right? Ooh. Now we just need to show that it's also in H. But you can give pretty much the same argument to show it's in H, right? Because what I just crossed out in purple shows that B inverse B inverse is in H. And of course, A is in H, right? Therefore, B inverse is in H. So thus, A inverse, B inverse is in H intersect K, which is equal to the identity by assumption. Therefore, A inverse, B inverse is equal to E. Then by star, we are done. Now, I know, I could look at my notes and I could go through this a lot faster, right? But I think it's good for me to stumble around and show you how you find proofs like this if you haven't memorized them ahead of time. Yeah. Thank the person that pulled the fire alarm earlier, right? I mean, I don't know. So, any questions? With this lemma in hand, the next theorem is a piece of pie. So here's the theorem. If G is equal to H internal direct sum with K, then G is isomorphic to the external direct sum of H and K. Right? So here, recall G equal to H direct sum K in our current discussion means what? H and K are both normal subgroups of G, and HK is equal to G, right? Where H intersect K is the identity. Them's the terms and conditions that come with H plus circle K. All right, that's all wrapped up into that notation. That's what I mean. So what's the proof? Let's get to it. So assume that H and K are as I just wrote them, and let's define phi of x comma y equal to, and so this here, what formula do we want to put there? It is x times y. That is the formula. The rest of you are like, oh, I could have said that. Man. Like, no, it's the cosine of x plus y. No, of course not. All right. So that is, in fact, a mapping from where? So here, phi is going from where? It's going from h cross k to g, yeah? I will show that that is an isomorphism. Okay? So let me actually start with the proof that it's onto by lemma oh man, no, I shouldn't. I'm an idiot. I shouldn't do that. Sorry, guys. Oh, yeah. No. I'm sorry. I'll get with it eventually here. If G is in G, which is equal to HK, then there exists an H and a K, little h and K, right? H and K such that what? Such that G is equal to H times K, right? Then what? Notice that phi of H comma K equals to HK equals to G, therefore phi onto. This is actually true independent of the normality condition or even the intersection being identity, right? As long as you have the product of the two subgroups is the whole group, the mapping that Emily just defined for us is a surjection. But the injectivity and the homomorphism property require the conditions that we wrote down. So let's look at that. So if we look at phi of x1, y1 times x2, y2, how do we do that? So the multiplication in here, how's it go? By definition, x1, x2, y1, y2, right? That's how we multiply in the direct product. And then by definition of phi, thanks to Emily, this is x1, x2 times y1, y2. Yeah? Where x1 and x2 are from h and y1 and y2 are from k. Now I use the lemma. What's the lemma allow me to do? Commute, right? So I can commute x1, y1, x2, y2 like that because in the middle I've got thing in h, a thing in k, a thing in h, a thing in k, and so those commute by part 2 of the lemma, right? But what's that? That is phi of x1 comma y1 times phi of x2 comma y2 homomorphism. You see that the commuting was mission critical to proving this is a homomorphism. How do I prove it's injective? What's the kernel of phi? I don't know. We can choose kernel. Let's not do that. There's no need to get. I mean, I have an unhealthy fascination with the kernel. We could just prove injectivity directly, right? Suppose phi of x1, y1 equals to phi of x2, y2. What happens? We get x1, y1 equals to x2, y2, right? Where x1 and x2 are in h and y2 and y1 are in where? K. So by the lemma, part 1 of the lemma, x1 equals to x2 and y1 equals to y2, which then implies that x1, y1 equals to x2, y2, which is what we need to show that phi is 1-to-1 and thus a bijection, since we already showed it was onto. Well, indeed, it's an isomorphism, right? So that proves the isomorphism. All right. You proud of me? I didn't bail until now. Yeah? At a moment of, uh-oh. It's better. Although I gotta be careful. If I pull this card too long, all of a sudden the internal console will tip over, and then we won't see anything. You're like, keep pulling. I don't mind class ending early. Let's see here. All right. I have to end early to go get Sprana. See, I say that, but I love teaching this class more than I love sabotaging Sprano's class. Now, once we have a test, and the next test, though, remind me, in the middle of the test to go harass him. All right, so I spent a long time with you guys today just proving up to this point. The results which follow after here are important, and maybe I'll prove one of them in the help session or something, I don't know. But where's my laser? That's the question. Oh, yes, here it is. So the next result is something we actually have already seen, right? The least common multiple of the orders is the order of the pair. Yeah? Remember that? There's the proof right there. Yeah, see it? So this, well, down here. If x and y have finite order and we have the pair x comma y in the direct product of g and h, then the order of the tuple is the least common multiple of the orders. This proof is right there. So we actually saw this in action in the example I just covered up, right? We have x, y well, excuse me, that's not in D3. That x comma y is where? Is it in D3? No. It is in the direct product of x generated subset and the y generated subset, right? That's an h cross k. That's a typo right there. Okay. Another application, if we look at the subgroup generated by 10, it has order 4 in Z40. The subgroup of order 10 in Z30, excuse me, this has that has order 4. This has order 10. Least common multiple of 4 and 10 is 20. So if we look at the tuple generated by the cyclic subgroup in Z40 cross Z30 generated by 4 comma 3, that has order 20. The next page is a master class on how to do a homework problem I've assigned you, or several of them, where the game we play is, if you're looking at the direct product of cyclic groups, and then you can start asking questions like, how many elements are there of a certain order? So then that question becomes, how can you get that order from the least common multiple of possible orders in the subgroups? So this is a combinatorial question, essentially. You just have to chase down cases. And so here I look at, for example, how to find elements of order 6 in Z6 cross Z2, right? So you can either have, what are your choices? You can have order 6 in the first one, order 1 or 2 in the second one, right? Or you can have order 3 over here and order 2 over there. There's 2 different ways of reaching least common multiple of 6. The next example is a little bit more exciting. Anyway, we talk more about these in the help session. Here's an application of that. If you look at Z100 cross Z25, you can count that it has 24 distinct elements of order 10, right? If that has 24 distinct elements of order 10, how many subgroups of order 10 are there? Well, remember, every subgroup of order 10 in a cyclic, I mean, this is in a cyclic, it's going to be a cyclic subgroup, as it turns out. So that means that subgroup order 10 has 4 possible generators, right? So if I've got a total of 24, that means that I've got 24 divided by 4, I got 6 subgroups of order 10. Each subgroup I have comes with 4 generators. So if I got 24 total generators, that means I got 6 subgroups, right? It's like counting the number of cows in a pen by counting the legs, right? So I like that's why I like counting subgroups of order 20. It's like like phi of 20 is 8, right? So that's like counting number of spiders by counting the number of legs, right? Although this breaks down at some point, because as you've seen, spiders lose their legs, right? You've seen it. It happens. This theorem right here is amazing. G and H are finite cyclic groups, then G cross H is cyclic if and only if the order of G and H are relatively prime. I should go over the proof of that with you guys at some point. So application, ZMN is isomorphic to ZM cross ZN if and only if M and N are relatively prime. So that's why Z6 is isomorphic to Z2 cross Z3, but Z8 is not isomorphic to Z2 cross Z4 because 2 and 4 are not relatively prime, whereas 2 and 3 are. This is the next step in this cavalcade of insanity, which is to define the direct sum for more than two things. Just like in linear algebra, it gets more complicated. You have to look at independence of the subgroup with respect to the complementary subgroups, all of them. And, but otherwise, it's pretty much the same song and dance. The same isomorphism is built. The lemma generalizes. It all generalizes to more than two products. And then finally, but it hurts to actually go through that. Here's the map. I count the number of elements of order 6 in Z6 cross Z3 cross Z4. That was unfun. You can generalize the, Z n1, n2, da, 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 nk is isomorphic to zn1 cross zn2, da, da, cross znk, only if they're all coprime, right? And then finally, I share with you guys at the end of this the fundamental theorem of finite abelian groups, which is that if you have a finite abelian group, it's a direct product of cyclic groups of prime power order, and the number of terms in the product orders of cyclic groups are uniquely determined by the group. So like if you've got a group of order p, it's zp up to isomorphism. For p squared, it's either zp squared or zp cross zp. For p cubed, it's this, or that. And that's pretty much it. Now, I will talk more about the end of this lecture in the help session, and maybe next time, but just wanted to throw it out there while we're here.